Hello there people, welcome back. This is a one mark question asked in GATE exam of 2014. Let's discuss it. They're saying let k is equal to 2 power n. A circuit is built by giving the output of a n bit binary counter as input to a n to 2 power n bit decoder. So we are using two devices in our circuit. First one is a n bit binary counter. Second one is a n to 2 power n bit decoder. Okay, let us assume that value of n is equal to 3. So they haven't given this diagram in question. I've drawn it myself just to explain this statement. We are assuming n is equal to 3. So how many outputs will n bit binary counter have? N only. Okay, so if n is 3, it will have 3 outputs. And how many inputs and outputs will a decoder have? If it is n to 2 power n, these many inputs will be there and these many outputs will be there. N means 3 inputs, 2 power n means 8 outputs because n is 3. 2 power 3 is 8. Okay. So we will get such a circuit. Now let's analyze this first device, which is a counter. What will this counter do? It will keep on counting 3-bit numbers. It will start from 0, 1, 2, 3, so on. It will go till the maximum number that can be represented in 3 bits. Okay, maximum value of a 3-bit binary number can be 7. That is 2 raised to the power n minus 1. Okay. So the counting sequence of given counter is this. 0, 1, 2, 3, 4, 5, 6, 7. And then again it will come back to 0. Okay. Again it will just keep on looping in these numbers. That means whenever you give a clock, it will increment the output by 1. If output is already 7, it will reset the output to 0. Okay, that happens when a clock signal is given. Now what is this decoder doing? It will just interpret this binary number and make that specific output high. Suppose at any given time the input to this decoder is 0. What I'm trying to say is, suppose this counter state is 0. 0 means all 3 bits will be low. This counter will sense that all 3 bits are low. That means this 3-bit binary number is equivalent to 0. So it will just keep its 0th output high. Okay, this is the 0th output. Its logic level will be 1. Okay, this output is high. Like this. Okay. Now whenever a positive edge of clock is given, this counter will increment the output. Earlier its output was 0. It will make its output 1. 1 in 3 bits means 0, 0, 1. Okay. This is going to sense that the 3-bit binary number in input is 1. Okay. These 3 bits represent 1. What it is going to do? It will make its first output high. So this is 0th output, this one is first. Okay. All of other outputs will be low. So it is 0, 1, 0, 0, 0, 0, 0, 0. Okay, like this. Now whenever I give a next clock signal, this is going to increment the output. Earlier its output was 0, 0, 1. You increment this number, you are going to get 0, 1, 0. Okay. So its output will become 0, 1, 0. This will get the same input. So input here is 0, 1, 0. This decoder is going to sense that this 3-bit pattern means 2 in decimal. Okay, 0, 1, 0 is 2. What it is going to do? It will make its second output high. So 0th, first, second. That means this output will become high. Okay, so this will go low and this output will become 1. So on as we keep on giving clocks. Now ignore this entire circuit. Just focus on these outputs. Initially this one was high. Initially when this circuit was just given some power, this one was high. When I gave the first clock, this one becomes low, only this one will be high. Then on next clock signal, only this one will be high, only this one, and so on. This last input will become high. As soon as this value is 7, upon giving next clock signal, value becomes low. Sorry, value becomes 0. 0 means again it will start from here. So what is happening? You can just see, you can just think like that. You have 7 LED lights. Okay, sorry, you have 8 LED lights. First, this one is glowing. All of these are off. Then this one is glowing, all other lights are off. Then this one is glowing, all other lights are off. What you will see is, you can see this glowing part is traveling like this and then coming back here. Traveling like this and then coming back here. So such circuits are used for decoration purposes and parties. Okay, I'm sure you have seen it. And this is how they are implemented. Now let us see which one of the options is correct. We have k-bit binary up counter, no. K-bit binary down counter, no. K-bit ring counter, yeah. It is a k-bit ring counter. Let us see what happens in a k-bit ring counter. K is 8. See, K is 2 power n, which is 8. So we have 8 flip-flops to make a 8-bit ring counter. What is happening? All of these are D flip-flops. I haven't written D here, but you just assume these are D flip-flops. Whatever is the input of D flip-flop, that will become the output. Suppose at any given point of time, the outputs were 0, 0, 0, 1, 0, 0, 0, 0. Okay, so these are the 8 outputs. So at any given time, our ring counter is in this state. That means, what is the equivalent state of this circuit? 0, 1, 2, 3. Third output is high. That means 0, 1, 2, 3. This output is high. Okay. What will be the respective input for this decoder? Or what will be the state of this counter? It will be 3. 3 means 0, 1, 1 and 0, 1, 1. Okay. What will be the next state of a ring counter? Whatever is this input, it will travel here. In simple words, all the bits will shift by 1 bit. Okay. So this 0 will move here. This 0 will move here. If all of the bits shift by 1 bit, this one will go here. Okay. So this output will become 1. And this 0 will go here. Okay. This one will become 0. Similarly, this last 0 will come here. So the next output is this just becomes high. Okay, so next output of this circuit is this one becomes high and the value becomes 4. Okay, it is 1, 0, 0. Here also the fourth output becomes high, 0th, 1st, 2nd, 3rd, 4th. Now let us analyze next output in both of these circuits. In this one, this 0 will come here. Okay, so I'm writing a 0. And this 1 will just shift by 1 more bit. Okay. Rest all bits will remain as it is. Or you can say they have shifted by 1 bit. But that's just saying as no difference because earlier also all other places were 0 only. In this, the 1 shifted by 1 place. What will happen in this circuit? In this circuit also, this output that was high will shift. That means now this one will turn high. It is 0th, 1st, 2nd, 3rd, 4th, 5th. It is the 5th output which becomes high. You can see both of these are working exactly same. When this one reaches on this last output, it will come back to 0th flip-flop. Okay, here also when this last output glows, it will come back to 0th after receiving a clock. So both of these circuits are equivalent. What about these numbers? Just neglect them. They are internal working of a circuit. Okay, see here, these are all the inputs and these are the outputs. In input, we only have a clock signal. This is the internal working. We don't have to care about it. These are the outputs. Here also, only input is this clock signal. Okay, so both of the circuits are equivalent. Your answer is k-bit ring counter. Okay, thank you very much.